Okay, hello. So the first video I put out was answering a question about the general rational function. So let's drop down. Let's talk about some cubic functions. So this is a pretty general question. It actually looks like a little cry for help, which is okay. It looks like the question is, please help. I don't understand anything about cubic functions. Okay. So if you watched the last video, I made a big point, and I'll reiterate it here that I'm not expecting you guys to be experts on any of this. Really the focus of bringing up these functions right now is to kind of put you in a state of mind where one, you acknowledge functions past linear are important and they exist, and there's an expectation you know some stuff about them. But really the focus is when you're looking at a function like cubics, there's certain amount of information that you should be able to tell right away. Now, I'm not saying this is necessarily recall from memory, but I am saying when you look at a function, you're doing analysis, there's certain information that will always be important. So if you notice on these assignments, I basically ask you the same 8 questions over and over again. That implies that those 8 questions are at least part of the analysis set you should do for all functions. Now in the future, whoever wrote this, or as you're writing more questions, I'm going to encourage you to be more direct and more specific. Like if you look in the question about rationals, that's a very specific question that I can target in a video. Cubic functions, you're basically asking me to go over the whole thing, which I'll do. I'm going to highlight very particular parts of it, which I think are the most important. But if I'm not answering your question in this video, please make sure you're reposting the question. So I am. So without further ado, let's jump in, talk a little about cubic functions, and see if we can gain understanding that's going to help us not only the exam, but for the year and beyond. So I'm pulled up the activity did in class the other day, just like the previous video, where I asked you guys to just kind of contribute and add some information. Oops. Add some information to the whole about cubics. So let's talk first of all like the term cubic, so we can gain an understanding of what the general form has to have, what the distinguishing characteristic of cubics has to be. So cubic, okay, actually implies a certain degree. And so cubic implies, in this particular case, a third power. And so if you ever have a function whose degree is out of 3, you have a cubic function. And so I'm actually going to drop down and talk about the parent function first. This is actually why the parent function of a cubic turns out to be, and I'm just choosing f because it's a standard kind of default notation, turns out to be f of x equals x to the third power. Now, x to the third power, that is what defines a cubic. So if you have a function, if you have any polynomial in which the degree is 3, then you're going to you can go ahead and qualify that as being a cubic function. Now we can compare that to the general function, which I'll put up here. Again, I'm just going to use f because it's a standard. F of x equals ax cubed plus bx squared plus cx plus d. That's our general cubic. Now, comparing that to the parent, which is just x cubed, the parent is the simplest version of the function. And so basically what we're saying is the only important part, the only part that makes it cubic, is this x to the third power. Now, if you notice, there is more to the function, obviously, but this part is basically a quadratic. The x to the cube part is what makes it this cube. Now, if we're going to sketch the parent graph of cubic functions, which I'll rewrite here just for reference, f of x is equal to x to the third power. We have to understand that this is going to have a pretty dramatic effect on our graph. This cubing of the function means we're going to take whatever x value you have and multiply it by itself 3 times. That's literally what the cube part actually means. And so like that will tell us, that will help us identify why it's actually unique compared to say like something like a quadratic. But maybe the best way we can see that is to throw into a quick table. So I'm not going to table all the values, but I want to look at some of them. So if I'm going to choose some x's, I want to graph some f of x's. So right here in the middle, let's just choose 0. Now if I put 0 in for x, f of 0, that's 0 times itself 3 times, that ends up being 0. So that means we do pass right here through the origin for the, in this case, parent graph. If I drop here and say pick a 1, 1 in for x, multiply it by itself 3 times, you end up with 1. Which means we should also examine, say, like -1. Now, if you take -1 and multiply it by itself 3 times, -1 times -1 times -1, we'll actually end up with a -1 as well. And so what we're seeing take place here is the characteristic shape of cubic functions. Unlike a quadratic that forms a nice symmetric U, which is formed, by the way, because squaring a value makes it positive, a cubing a value, it does still allow for negatives to be part of the range set. So we have 1 and -1, so there is like some level of symmetry, but it's not going to be symmetric, say, as in that parabola shape of a quadratic. If we pick 2, 2 cubed is 8. If we pick 2, or sorry, -2 and cube it, we get -8. So again, we're seeing some level of symmetry here, but not in the order of, say, like the quadratic function. So if I graph 2, 8, and 2, -8, again, we can start to see this like nice characteristic S curve come to life. Now, this I can't graph any more values that are actually on this grid because there's not enough room, but this is enough, I think, to kind of give us a sense of what the graph should look like, which is this S. Now, I mentioned before that in the general cubic function, oops, in the general cubic function, although the characteristic part was a cubic, we do actually have a quadratic component as well. Now that does play out here in the parent graph. If you can imagine, I'm just going to draw this in a highlighter. If this was a quadratic, it would come back up in that parabola shape. But since you do have a cubing here instead of a squaring, you allow for negative numbers, and it's almost like you're able to flip the negative part of the graph down. And so like there is a relationship there to maybe functions we've seen in the past, but this is what gives cubics their characteristic S shape. Let's see. Let's try to do this one. So now this equation, or sorry, the equation for this graph, I should say, is not as simple as y equals x cubed. Now it does include an x cubed, because again, you do see kind of this characteristic S shape where it starts at negative, ends at positive. But since the other terms of this function aren't 0, it's going to take like it's going to have a square and a x term as well as a constant. You see like this S very much exaggerated. Again, I'm not asking you to be an expert at this right now. It's just something I want you to notice. What's interesting about this function is that it has very interesting kind of middle behavior, but the end behavior is very easy to determine. There are no asymptotes because there's no number that this cannot cross. It can take all x values, it produces all y values, but it does have zeros, it does have y-intercepts. Now, y-intercepts are nothing more than where it crosses the y-axis. So this point right here at 0, 3 does serve to be our y-intercept. Zeros are defined to be the parts that actually make the function value 0, hence the name 0. Another way to say that is when it actually crosses the x-axis. X-intercepts are synonymous with the idea of zeros. So this particular function, we actually have 3 at -1, 0. We have one at 1, 0, then we have one at 3, 0. So this is something we've been kind of dealing with since, say, 8th grade / Algebra 1, where you're looking for where these functions, although at that level you're probably just limited to quadratics and linears, cross the x-axis. In this case, there are 3. Now, if you want a hint at the future where this is all going, it's very predictable you had 3, because if you look at the function, the degree value is 3. And so there is a connection there, as one will explore much in detail later on. Now, the question here asks for end behavior. All end behavior is indicating is that it wants to know what happens as x gets very big or x gets very large. In other words, as you go to one end of your domain or the other. And so like this part is going to help to determine our end behavior. In this particular case, the end behavior, it looks like as x is tending towards infinity, so in other words, as we get bigger and bigger x's, y is going to tend towards infinity as well. This arrow is pointing up, indicating that it's going to keep increasing. That's how I'm getting the infinity part for that particular one. On the other end of things, so we do have to examine both end behaviors. This tends to dive down. And so we can say as x gets very small, tending towards negative infinity, y is ending up, in this case, at negative infinity as well. In other words, it's going to keep going down. So that's another very important thing to think about when you think about cubic functions, is you have to examine all parts of it, not just what's happening kind of in the middle, but also what's happening at the very ends. This is going to become second hat for us as the year progresses. It's just something I want in your head now, so it's going to become second nature later. This is basically the pre-study of calculus right now. Calculus is really just talking about function behavior. That's really more or less what the study is. And so this is definitely a big exercise to help you get started with that. Uh, let's talk one more thing. We need domain and range of this function. Now, the notation of how you use domain and range is up to you. I'm not going to force you to use one or the other, but I'm telling you right now, from my experience in college, you have to be kind of fluent in all forms. Different professors will use different things, different teachers do different things, but in the end, you have to just have a sense of like, I'm trying to convey this idea of how many x's, what x's I can use and what y's are produced. The notation itself, like I said, is going to be variable, so you just have to kind of attach yourself to whichever one you want, but also be able to read the rest. Now, if we're looking at this function, the end behavior actually tells us a lot about what the domain and range are going to be. So if you look at the x's, it's going to range from it's going to go from negative infinity to infinity. And if you look at the y-end behavior, the lower end behavior is at negative infinity, the upper end behavior is at infinity, which means our domain and range will be all real numbers. Now, how you write that, again, completely up to you. My preferred method, the one I think you'll see at the collegiate level more often than not, is going to be in set notation. And so if we talk about the domain, we're going to talk about the x numbers. Now, the squiggle line bracket thing, it just tells us we're talking about a set of numbers. What is inside the squiggly brackets is a definition of those numbers. And so this first part tells us what we're actually looking for, in this case, x's. This line now indicates to the reader that I'm here to define x's really well. And so let's use maybe some inequality notation in here. And so the x value is going to be less than infinity, since we can never reach it, but at the same time be bigger than negative infinity, which we can't reach either, and we'll close it up. Now that just tells you what this graph told you up here, that the x values are going to range from negative infinity to infinity. In fact, we're going to use all of them. This is just, again, a proper way to write it using set notation. Now, alternatively, you can also just use intervals. Now, interval notation looks suspiciously like chorded pairs, which is why I never tend to actually like it, because it seems to be a little confusing. But if you like it, that's fine. The first part tells us whether or not we can actually use a number. A curved bracket says we cannot use a number. We put the smaller end of the domain on one end. So this says we're going to start at negative infinity, comma, end at infinity, and we can't reach that one either. And so these two actually say the same exact thing. This isn't the coordinate infinity, infinity. This tells you you're going to start at negative infinity. Curved bracket says we can't use a number, comma, end at infinity. Curved bracket means we can't use a number. Now the same is going to hold true for range, so this is actually just going to be like a direct copy, except now we're talking about y values. So you can define the range to be the set of all y values, such that y is smaller than infinity, but bigger than negative infinity. Or again, if you want to use bracket notation, we cannot use a value, but it starts at negative infinity, ends at infinity, we cannot use a value. And so that's more or less the big piece of information you should always have or think about when you think about a function. Now this part down here, it's a bit of a curveball because I haven't asked you to do it yet, but I want to again start thinking about how this graph looks and behaves under specific values. So if you think about this being the parent function, you think about this being an example of an expanded version of the parent function, and you think about the end behavior, you can think of this as basically a function that starts low, excuse me. Let's change this up a little bit. You can see this as a function that starts negative and ends up positive. That's the general flow of it. So we start negative and positive, which means that if I'm taking any version of this function, knowing that x cubed is the controlling piece, and I keep that x cubed positive, so let's say 4x cubed, it doesn't really matter what I put behind it. This is still going to have the general start negative and positive behavior. Okay, I might have some weird stuff in the middle, but I don't really care about that. I'm talking about end behavior. So again, this leading term that has the degree and the leading coefficient, that controls the shape of the graph. So if I want something with different end behavior, I have to change this coefficient. Now I can't change it just to a bigger or smaller number. I actually want to flip the graph. So if you recall from your previous algebra classes, I can accomplish that by taking the opposite value of the coefficient. In other words, if 4 is positive in this one and I want to flip it around, I got to make that leading coefficient negative. So like negative 2x cubed, and again, it doesn't actually matter what I put after it. Because of negative 2x cubed, you can assure that I'm going to be able to flip the end behavior. So that was more or less a bonus extension question, but again, just trying to draw on the things that you know before, because in the end, that's really what upper level math does. It takes simple ideas, forces you to generalize them, and then applies those ideas as usable tools into direct applications which you might have to mix other knowledges in with. And so that's kind of where this is. You have to mix your knowledge of how graphs work in general to the generalized form of the cubic function. That's all math really is at all. So there was no specific question asked about cubic, so I kind of talked through an overview. I more or less recreated the key, maybe aside from these things, but I was really talking about these pieces while I was talking about the function itself. Like the argument is really just the x value. So like that's the argument right there, the x. The argument, another way to say the argument is the independent variable. Typically that's the x. The degree of the function is the highest power in the function. In this case, it's a degree of 3. Leading coefficient is the number in front of that x, the leading degree x variable. The variable terms, constant terms, are just the difference there is the ones that have an x in them and the one that doesn't have an x in them, which is going to be true not just for cubics, but pretty much everything, right? So I hope I answered your question there, or at least make you feel a little better about cubic functions. Again, I'm not expecting you guys to be experts. I'm just asking you to know a little bit about them in terms of like the basic information you should know for all functions. If that didn't answer your question, feel free to ask me another one in class, post it to the wall, post it to Schoology, anything you can do to get that question you need answered. Come talk to me at Before School, After School, Math Lab 4A, or Spartan Time when it finally opens up next week. We'll make you sure that you're as comfortable as you possibly can be with this material, all right? So thank you for watching. Sorry that was a long video, but that's what happens if it's not a specific question. I'll see you guys in the next one.